Hello and welcome. Today we're jumping right into the massive quest for limitless clean energy. And it's a story about a huge scientific revolution, but it all kind of boils down to a surprisingly simple question, a question of shape. So get this, what if the go-to design in fusion research for more than 50 years was suddenly being challenged by something that looks, well, a lot like a cored apple? Yeah, it sounds a little weird, I know. But this one change in geometry could actually be one of the most important steps we take in our journey to harness the power of the stars. Okay, let's really get into this.
For decades, scientists have been chasing what is basically the holy grail of technology, fusion energy. I mean, the dream is to build a miniature sun right here on Earth.
Okay, so the basic idea is this. You take a fuel, usually some form of hydrogen, and you heat it up to temperatures that are just insane. We're talking hotter than the core of the sun, over 100 million degrees Celsius. At these temperatures, the fuel turns into a plasma, and the atoms are moving so fast they can actually fuse together, releasing a tremendous amount of energy. The problem, of course, is how in the world do you hold on to something that hot?
Well, for most of the history of fusion research, the leading design for containing that plasma has been a machine with a very specific and pretty familiar shape. It's called a tokamak, and a tokamak is, at its heart, a magnetic bottle. It uses these unbelievably powerful magnets to trap the plasma in a stable, donut-shaped loop. This keeps it from touching the reactor walls, which, they would just vaporize instantly.
Now, a really key design feature for any tokamak is something called its aspect ratio. It sounds complicated, but it's just the ratio of the whole donut size compared to the thickness of the plasma ring inside. Really, the easiest way to picture it is, the aspect ratio tells you how big the hole in the middle of the donut is.
And for years and years, the standard design has always had a high aspect ratio, somewhere around 2.5. That means you get a relatively thin ring of plasma and a big, obvious hole right in the center. For a long time, that was just how you built a stable tokamak. But what if you didn't need that big hole? What if you tried to shrink it?
So back in the 1980s, a new idea really started to take hold. And it was one that basically flipped all the conventional thinking about aspect ratio right on its head. And this is where the spherical tokamak, or ST, comes in. The idea is so simple, but it's totally revolutionary. You just shrink the central hole of that donut as much as you possibly can. And when you do that, the donut gets all squashed down until it's almost a sphere, or as it's perfectly described, a cored apple. Now, this wasn't just a wild theory. The idea was first put forward by a guy named Martin Peng in 1984. Then, by 1991, this small, kind of scrappy experiment over in the UK called START was built just to test it out. And the results? They were absolutely stunning. After they upgraded it, START just began shattering performance records, proving that this whole cored apple shape had some seriously incredible advantages. So this is the big question, right? Why does just squashing the donut make such a massive, massive difference? Let's put these two shapes head to head and see what's going on.
Okay, so on one side, you've got your conventional tokamak, high aspect ratio, around 2.5, that classic donut we all know. And on the other side, the spherical tokamak with a super low aspect ratio, sometimes as low as 1.2, giving us that cored apple shape. And this seemingly tiny change, it has profound effects on how the machine actually performs.
To really understand that performance difference, we need to talk about one specific number. It's called beta. All beta is the ratio of the plasma's pressure pushing outwards compared to the magnetic field's pressure squeezing it in. A great way to think of it is as the bang for your buck you get from your magnets. A higher beta means you're containing more plasma for less magnetic field energy, which, as you can imagine, is a huge deal for cost and efficiency.
And right here is where the power of the spherical tokamak just becomes crystal clear. The record beta for a conventional machine was about 12.6%. That little START experiment, it achieved a beta of 40%. I mean, that's not just a little better. That is a game-changing leap in efficiency. We're talking more than 3 times better.
So how does it do it? Well, that compact shape makes the plasma way more stable. The physics of it just means the plasma naturally stays in a good magnetic region, which helps suppress some of the most dangerous instabilities that can just kill a fusion reaction in an instant. It lets the machine operate way beyond the normal stability limits of a conventional design. And all of this points to a machine that could be simpler, smaller, and a whole lot cheaper to build.
But, and this is a big but, it is not a magic bullet.
The ST design has its own set of major engineering headaches. For one, that super-thin central column is incredibly hard to shield from the intense neutron radiation flying off the fusion reaction. This means it would degrade and have to be replaced, maybe even once a year. You also can't really fit superconducting magnets in there, which means you lose power. And the whole design kind of relies on some really complex plasma physics to run efficiently.
So, with all these pros and cons on the table, where does the spherical tokamak actually fit into this grand quest for fusion energy? Look, the spherical tokamak isn't guaranteed to be the final answer, but what it does represent is a hugely important alternate path. Its potential for way higher efficiency in a smaller, more compact device could dramatically slash the cost and the complexity of fusion development, and that could speed up the entire field.
And really, that's the key takeaway. It's summed up perfectly in the research that came out after START's incredible success. The ST represents a new and fundamentally lower-cost way of tackling one of the greatest scientific challenges humanity has ever faced.
Which leaves us with this one final, really fascinating question. After all these decades of focusing on the donut, could it be that this compact, efficient, apple-like shape is what will finally let us bottle a star here on Earth? The research is pushing forward, but the potential is just undeniable. Thanks for tuning in.